These are the answers to the Chapter 16 practice quiz, starting with multiple choice questions. Number 1. Which of the following choices represents a Bronsted-Lowry acid that is paired with its conjugate base? On page 655, you can read about a definition of the conjugate acid-base pair, and it says that every acid has a conjugate base formed by removing a proton from the acid. So the problem with choice A is that you're actually adding a proton instead of removing one. The problem with choice B and D is that you're actually removing 2 protons to go from the acid to the conjugate base. So the correct answer is choice C. If you remove H plus from that particular formula, then you will get the conjugate base. In number 2, we're given a reaction and we're told that it is observed to proceed spontaneously to the right, and we have to decide which is the stronger base in the system. Take a look on page 657, and you can see an example of a reaction between HX and water. And it says if water, which is acting like a base, is the stronger base than X minus, then the equilibrium lies to the right. But if X minus is a stronger base than water, then the equilibrium lies to the left. In every acid-base reaction, equilibrium favors the transfer of the proton from the stronger acid to the stronger base to form the weaker acid and the weaker base. So because this reaction is observed to proceed spontaneously to the right, that means that the value of K for this reaction is greater than 1. So the correct answer is either B or D. On the left we have an acid and a base, but since the reaction is driven to the right, then carbonate, CO3 2-, is the stronger base. So correct answer is B. In number 3, we are given a polyprotic acid. We're given 3 K values, Ka1, Ka2, and Ka3. And then we have to determine in this particular solution between sodium dihydrogen phosphate and sodium hydrogen phosphate, which of the following species is present in the solution at the lowest concentration. To help us answer this question, take a look first on page 674, where it talks about polyprotic acids. It says, note that the Ka2 is much smaller than the Ka1. We can see on page 674 a variety of polyprotic acids. One of them that I've highlighted here is carbonic acid. And on page 675, they use the Ka1 to calculate the concentration of H+, and they get 4 times 10 to the negative 5. Then they go on to calculate the concentration of the carbonate ion, which comes from Ka2, and they mention that this value, 5.6 times 10 to the negative 11, is very small, showing that our assumption was justified that the ionization of HCO3- or hydrogen carbonate is negligible relative to that of H2CO3. However, it's the only source of carbonate ions which has a very low concentration in the solution. So why do I mention this example? Because if you look at the smallest value of K, in this case 4.5 times 10 to the negative 13, that means that the product PO4 3- must be present at the lowest concentration, since that particular K is extremely small. Questions 4 through 7 refer to the following table. The pH of solutions of 4 acids prepared at various concentrations were measured and recorded. Question 4, for which acid is the value of the Ka the smallest? Well, the weakest acid is going to have the lowest Ka value, and the weakest acid has the highest pH value for a given concentration. So based on the information in the table, the correct answer is A, acid 1. Question 5, which of the 4 acids is hydrochloric acid? Since hydrochloric acid is a strong acid, we're looking for an acid who has the lowest pH for a given concentration, so the correct answer is B, acid 2. Now suppose that acid 1 is written as HX. which of the following species has the greatest concentration in a 1 molar solution of acid 1? So acid 1 is a weak acid, and as you can see in this particle diagram, a weak acid has molecules that only partially dissociate. So the majority of the molecules have not lost their hydrogen ion. That means that HX is going to be in the greatest concentration. So correct answer is C. And now number 7, this has to do with which acid is going to require the greatest volume of titrant in an acid-base titration. Well, in acid-base titration, this goes back to chapter 4 on page 146, deals with molarity and stoichiometry and the amount of titrant, in this case sodium hydroxide, that is needed to reach the equivalence point is not based on the strength of the acid, but rather based on moles, molarity, and stoichiometry. Since all 4 of the acids have the same concentration, then they will require the same volume of base to reach the equivalence point. Question 8 gives us 4 different salts, and we have to decide which one has the highest pH. On page 678, it says that anions of weak acids is one example of a weak base. On page 681, it mentions that if the anion X- comes from a strong acid, then it's going to be neutral, so it does not affect the pH of the solution. On page 682, it mentions that certain cations like ammonium, which is the conjugate acid of a weak base, is acidic. It mentions that alkali and alkaline earth metals are neutral and do not affect the pH. And we see this diagram in which iron can be slightly acidic. So choice D is acidic because it contains iron ions. Both lithium and chlorate are neutral. Potassium and bromide are neutral. But the nitrite ion, which comes from a weak acid, HNO2, nitrous acid, the nitrite ion is the conjugate base of a weak acid, so it behaves as a base in solution. Here we have a 1 molar solution of ammonium chloride. We have to decide if that's an acid or base. We should know that ammonium is a weak acid. So that means that our choice is either A or B because the pH should be less than 7. So ammonium acting like an acid, correct answer is choice A. Number 10. We know that the solution has a concentration of 0.1 moles per liter. We know the pH is 4. We have to determine the value of Ka. So here is our generic Ka expression. If the pH is 4, that means that the concentration of H plus is 10 to the minus 4. The concentration of A minus is also 10 to the minus 4. And on the bottom we have the concentration of HA, which is 0.1, and then again we would subtract that little bit. But since to make our math easier without a calculator, let's go ahead and ignore that little bit. So we have 10 to the negative 4 squared divided by 0.1. This gives us 10 to the negative 8 divided by 10 to the negative 1. So negative 8 minus negative 1 is negative 7. Correct answer is C. In number 11, we are given the Ka value. We're also given the concentration of the weak acid. We have to figure out approximately the pH. So here we have the Ka expression. It's equal to 4 times 10 to the negative 4. We can plug in our concentration of nitrous acid on the bottom. So we have x squared on top, and we have 0.01 on the bottom, since we can ignore the fact that x is relatively small. So we're going to go ahead and multiply both sides by 0.01. X squared equals 4 times 10 to the negative 6. We can go ahead and take the square root. That's a perfect square, so we get x equals the concentration of H plus, which is 2 times 10 to the negative 3. Now how can we estimate the pH since we can't use a calculator? Well, if the concentration of H plus were 1 times 10 to the negative 3, the pH would be 3. If the concentration were 10 times 10 to the negative 3, which is the same as 10 to the negative 2, the pH would be 2. Since our concentration of H plus is falling somewhere in between those numbers, then our pH falls between 2 and 3. For number 12, we are mixing 200 milliliters, or 0.2 liters, of a 3 molar solution of sodium hydroxide, so 0.2 times 3 is 0.6, 0.6 moles of sodium hydroxide, or 0.6 moles of hydroxide ions. We're mixing that with 700 milliliters, or 0.7 liters, of a 1 molar solution of HCl. So we have 0.7 moles of HCl, 0.7 moles of H plus ions. H plus reacts with OH minus to make water, but we still have an extra amount of H plus. So the amount of excess H plus is 0.1 moles, and that would be dissolved in a total volume of 900 milliliters, or 0.9 liters. So to estimate 0.1 moles divided by 0.9 liters, that's approximately 0.1 moles per liter, and the negative log of 0.1 is 1. So the pH of our solution is approximately 1. In number 13, on the right side of the screen, we can see there are 2 acids whose Ka values are known. On the left side of the screen, we see the conjugate bases of these acids in the form of sodium salts. So on page 656, it says the stronger an acid is, the weaker its conjugate base is. Well, who's the stronger acid? CF3CO2H. Since CH3CO2H is the weaker acid, that must mean that CH3CO2Na, that is going to be the stronger base. So solution 1 would have a higher pH because CH3CO2- is the stronger base. In number 14, we're given the autoionization of water, and we know that that normally has a value of 10 to the negative 14 at 25 degrees Celsius. So pKw is normally 14, but the pKw varies with respect to temperature. So how does the value of Kw change as we increase the temperature? Well, the Kw is 10 to the negative 14.9 when it's 0 degrees Celsius, and the Kw is 10 to the negative 13.5 at 40 degrees Celsius. So the value of K is increasing as the temperature increases. When a reaction shifts toward the products with an increase in temperature, then we know it is endothermic. So this reaction is endothermic because K increases as temperature increases. So the correct answer is not A. Also, we get the pH by cutting the pKw in half. So at pure water at 25 degrees Celsius, the pH is 7. However, at other values of temperature and other values of pKw, the pH of water is not necessarily going to be 7. So the correct answer is either C or D. Let's take a look at the temperature of 30 degrees. What's half of 13.8 is 6.9. So the pH of water would equal 6.9. So as temperature increases, the pH of pure water decreases. In number 15, we have 2 different concentrations of acetic acid, which is a weak acid. We have 2 different pH values, and we have 2 different percent ionization values. Consider that the percent ionization is going to increase as the concentration of the acid decreases. So here we see that at a lower concentration of acid, there should be a higher percent ionization. So the correct answer is either B or D based on the fact that 0.001 molar acetic acid has the higher percent ionization. Now, a more dilute concentration of acid would lead to a higher pH. A more concentrated acid solution would lead to a lower pH. So correct answer is D. And now on to number 16. We have two different Lewis electron dot diagrams, and we're looking at the difference between HClO3 and HClO2. On page 685, they talk about a variety of factors affecting the acid strength, including the polarity of the bond, the bond energy, as well as the general stabilization of the conjugate base. Here it's this idea of stabilizing the conjugate base that they discuss on page 685. It says many oxyacids contain additional oxygen atoms, and that helps to pull electron density from the OH bond, increasing the polarity and stabilizing the conjugate base. So the correct answer is that HClO3 is the stronger acid, and it's because of the stabilization of the conjugate base. Okay, now on to the free response questions. In number 1, part A, we have to draw the Lewis electron dot structure for propanoic acid, which contains the carboxylic acid group. On page 688, you can see examples of the carboxylic acid group. So we have to have a carbon with a double bond to an oxygen and a single bond to an OH. So that's our skeleton with 3 carbons, and there's our carboxylic acid group. So the rest of the molecule contains just hydrogen atoms like this. Alright, so that's our structure in part A. For part B, we have to write the chemical formulas of the two products. Since the propanoic acid loses a proton and transfers it to water, we get hydronium and we get the propanoate ion, which is the conjugate base. So one acid-base pair is that propanoic acid is the acid and propanoate is the conjugate base, and then water is behaving as a base, and the conjugate acid for water is the hydronium ion. In part D, we have to write the expression for Ka for propanoic acid. That's going to be concentration of hydronium times concentration of propanoate divided by concentration of the original propanoic acid. To calculate the value of Ka, we start with 2.79 is our pH. That will get us the concentration of hydronium, which is 10 to the minus 2.79, or approximately 0.0016 moles per liter. I'm including a couple of extra digits for precision because I haven't rounded off my final answer yet. Based on the 1-to-1 mole ratio between hydronium and propanoate, the concentration of the conjugate base, propanoate, is the same as that of hydronium. And then our concentration of propanoic acid equilibrium is 0.20 minus that small bit that dissociates, so it's pretty close to 0.20. It's around 0.198. Plugging in all 3 of these values into the Ka expression, we solve for Ka. And so we do the math, and we get around 1.3 times 10 to the negative 5 for our value of Ka. For this next part, we're going to calculate the percent ionization. So the percent ionization is defined as the concentration of H plus divided by the original concentration of the acid. So we have 0.0016, and again a couple of extra digits here, concentration of H3O plus or hydronium divided by the original concentration of the acid, and we get 0.81% for our ionization. Should the pH of sodium propanoate be equal to 7, less than 7, or greater than 7? Well, since propanoic acid is a weak acid, that makes propanoate a weak base. So to prove that, the pH should be greater than 7. It is a weak base. Let's show propanoate reacting with water as a base to produce hydroxide ions and the original propanoic acid. So the conjugate base of propanoic acid is propanoate. In part H, they want us to determine if a solution of HCl, which happens to have the same pH as 0.2 molar propanoic acid, will this concentration of HCl be equal, less than, or greater than 0.2? Well, it's going to be less than. I think you know that because it's a strong acid. So therefore you would need much less of it in solution. And you can determine that by doing 10 to the minus 2.79. So the concentration of HCl would be around 0.0016. Question 2, we're talking about carbonate acting like a base. So carbonate will accept a proton from water to make hydrogen carbonate and hydroxide. The Kb for this reaction will have concentration of hydroxide times concentration of hydrogen carbonate over the original concentration of the carbonate. We exclude water from that equilibrium expression. All right, we've written the Kb. Let's go ahead and calculate the concentration of hydroxide. Since the pH is equal to 11.62, we do 14 minus that value. So now we have the POH, and the concentration of hydroxide is 10 to the minus 2.38, and that works out to be around 0.0042 moles per liter. Well, let's go ahead and calculate the value of Kb. Since we know the concentration of hydroxide, it's also the same as the concentration of hydrogen carbonate, and the concentration of the carbonate ion is 0.1 molar minus that small little bit that ionizes. So plugging those numbers into the Kb expression, we get Kb is equal to 1.8 times 10 to the negative 4. In part E, the conjugate acid of the carbonate ion is hydrogen carbonate. Therefore, we can go from Kb to Ka by simply doing 10 to the negative 14 divided by the Kb, gives us a Ka value of 5.6 times 10 to the negative 11. All right, in part F, why would bubbles of gas be produced when sodium carbonate is mixed with a strong acid like nitric acid? Well, the carbonate reacts with the H+ ions in the acid to produce hydrogen carbonate, which breaks down rapidly into water and CO2. Number 3, we have a weak acid, acetylsalicylic acid, also known as aspirin. We're given a Ka, and we have to find the pH of 0.075 molar acetylsalicylic acid. So let's set up our Ka expression. Let's put in X and X for the concentration of hydronium and the conjugate base. Let's put in 0.075 minus X, and then we have to set that equal to the Ka, which is 3.0 times 10 to the negative 4. Notice that I made the simplifying assumption on the bottom that the minus X part can be ignored because X is relatively small. When we solve for X, we get that the hydronium concentration is 4.7 times 10 to the negative 3, and we do the negative log of that value, and the pH is equal to 2.33. Now on to part B. We have the same Ka expression, but this time they've given us a ratio of A- to HA. So the ratio of the conjugate base to the original acid is 1.5. Therefore, Ka is equal to hydronium times 1.5. Hydronium is equal to 2.0 times 10 to the negative 4, and the negative log of that is going to give us a pH of 3.70. All right, well, I think that represents the end of the Chapter 16 practice quiz. I hope that those answers were helpful. Thanks for watching. Good luck studying.